We've been studying pulsars and in our deaths of stars, and so this is a real radio telescope observation of a pulsar. This is pulsar PSR 0809 plus 74. This is a different pulsar, PSR 0950 plus 08. PSR stands for pulsar, and PSR 0329 plus 54. The numbers represent or tell us the location of these in the sky. We have three different tracks here. These were made by a strip of paper with three needles, and the needles would vibrate back and forth, and when a pulse came through, the needle would vibrate. And so the pulsars are rotating, and when that beam of energy points toward the Earth, we get a pulse. So we would get a pulse, a pulse, a pulse as this rotates around, and so we can measure these. So here you see a pulse and a pulse and a pulse. Here at this frequency, these pulses are a little bit easier to see, and at these frequencies they're a little bit harder to see. Here's a pulse, and I've circled that one. There's a pulse. So we're going to be doing two things with this observation. You're going to measure the period of time it takes these pulsars to rotate. Remember, it's very quick. These things pulsars are about the size of a city. They rotate incredibly fast. So we're going to measure the period of rotation. We'll also measure the distance. If you'll notice that the pulses don't arrive at the same time. So through interstellar space, there's a little bit of gas, a little bit of dust, and different frequencies travel through that at different rates. So it's kind of like we're going to have a race between two cars. I know they look like fingers, but imagine they're cars. This one's going faster, so we get to the start line at exactly the same time. If this is the finish line, this car is always going to win because it's going faster. But it's just going to win by a little bit. If the race is a little bit longer, then this car will win by a bigger gap. And if the race is a little bit longer, then this car will win by a much bigger gap. And so the difference in when the first wave arrives and the next wave arrives gives us the distance. So we're going to do two things. But in this video, we're just going to talk about how to measure the period of rotation. So I've given you the observation, and I've given you a data sheet to record it on, and I'll show you how to do that calculation. So the period of rotation is measured by the time it takes to go from one pulse to the next pulse. Well, I can't measure time directly here, but I can measure the distance on the paper. And you'll notice that there is a legend down here at the bottom, and so we can measure that. I'm not putting 0 here because it bangs into the document camera, so I'm just going to put a centimeter line, and I like these plastic rulers because you can look right through them. So we're going to call this 0, so this would be 1 centimeter, 2 centimeters, 3 centimeters, 4 centimeters, 4.1, 2, 3, here's 4.4, and 4.5, and our next mark is between 4.4 and 4.5 centimeters. We're going to measure this, though, in millimeters. So this is 10 millimeters. Each one of these little marks is a millimeter. So this is 10, 20, 30, 40, 45 millimeters. So that was actually between 44 and 45 We'll call that 44.5 millimeters. Let me show you that again. Okay, we're measuring from one mark to the next mark, and each little line, so here's 10, 20, 30, 40, 44, and 45, and this mark is between them, so I'm going to call this 44.5 millimeters. This number is going to allow us to convert from distance into time. So now I'm going to measure from one pulse to the next pulse. I'm going to put my ruler, put a centimeter mark right here, a long mark right here at one pulse, right at the very tip. And I'm going to measure the distance to the next pulse. So this is 10, 20, 30, 10, 20, 30, 40, 50, 55, 56, 57, 58, maybe a little bit more than 58, about 58.5 millimeters. I'm going to do the same thing from measuring from one pulse to the next pulse. So here is 10, 20, 30, 40, 50, 55, 56, 57. This looks like to be exactly on 58, so I'm going to call that 58.0 millimeters. And again, from one pulse to the next pulse, so there's 10, 20, 30, 40, 50, 55, 56, 57, 58, exact, just beyond 58. Let's call that 58.2. And that would be millimeters. So that's our measurement. To measure the period of rotation, we're going to measure from one dot to the next. So on your data sheet, we know that from 1 second to the next, we measured that to be 44.5 millimeters. On the top line, from one pulse to the next, we measured 58.5 and 58.0 and 58.2. And now we have to convert these into seconds. So we know 1 second is represented by 44.5 millimeters. These are all bigger than 44.5, so this is going to be a little bit bigger than a second. So to convert these distances into seconds, you're going to divide by the 44.5 conversion factor. So 58.5 divided by 44.5 is, we're going to round off to 3 decimal places, 1.315 seconds. And then this was 58.0. We're going to take 58.0 divided by 44.5. That's 1.303 seconds. And then the last one is 58.2 divided by 44.5, 1.308 seconds. And then our final answer for the period will be the average of these three. So I'm going to add 1.315 plus 1.303 plus 1.308 and divide by 3. Add them up and divide by 3 because they're 3 numbers. And so 1.309 seconds is the period of rotation for this pulsar. Okay, so I've done the first one for you. You'll do the other two. I will give you these distances. I will measure these for you, and I'll give you this conversion, and then you can convert those into actual second. You're measuring the period of rotation for a pulsar, and 1.3 seconds for something the size of a city. That's rotating incredibly fast.